So today we will concentrate on laws of thermodynamics. Actually, we will introduce those laws and we'll understand how those laws are very important with respect to material behavior or material property evolution. Okay, so first of all, you should understand that thermodynamics actually consists of four essential laws which govern the study of energetic transitions. So, what is energetic transitions? There are a lot of things from work to heat transformation or heat to work transformation may happen, or sometimes potential energy to kinetic energy transformation may happen, or sometimes there will be a scenario where different kind of transformation of one form of energy to another form of magnetic to electric, electric to magnetic. So all those energetic transitions can be understood if we understand the laws of thermodynamics. And another important thing, another important aspect of the thermodynamic laws is that relationship between thermodynamic properties. Now question will come, what is the thermodynamic properties, but what are the thermodynamic properties? Thermodynamic properties is belongs to different scenario where the initial state or initial condition of the system will be known, and you will take care of based on certain properties what will be the final scenario or final state, and from that initial position to final position the feasibility and stability, if you want to explain based on certain certain parameters like energy and free energy and all those things, if we consider, then this kind of relationship between those parameters, it belongs to certain properties of that system, and this kind of properties we can termed as thermodynamic properties, or sometimes we can tell that thermodynamic state variables, thermodynamic state variables. And the word in thermodynamics used to use that is system. And what is system then? A system is a part of a universe what you are considering when you are working on certain problem. So in a formal way, you can tell that a system is a part of the universe under consideration. A real or imaginary boundary separates the system from rest of the universe. So you can construct a real or imaginary boundary which actually separates the system from the rest of the universe, which is referred sometimes environment or sometimes surroundings. So system, what is system? System is a part of universe where you are concentrating or you are considering the part of this universe, and you are studying that part of the universe. So that's why that is a system of study or system of consideration. And other than the system, rest of universe, you can tell that it is the environment with respect to that considered system or the surroundings. So a useful classification of thermodynamic system can be identified based on the nature of boundary and the flow of matter, energy, entropy across the boundary. So if you see that here there is a system. What is system? You are considered this system to do certain investigation, and then this can be imaginary or real boundary, and across the boundary mass, energy or entropy, based on the entropy transfer you will define different system. So if you are considering open system, This is the one kind of system. In case of open system, system and surroundings can intertransfer mass and energy both. So if a system can interact with its surrounding with respect to transferring mass and energy both, then we can tell that system is open system. And go another extreme, that if a condition is such that no energy, no matter can interchange with the environment or surroundings, then the system is said to be isolated system. So here no mass, no matter will transfer from system to its surrounding, and no energy, no mass will transfer from system to surrounding. In this case, it can be told that it is an isolated system. So two extreme cases are there. One is open system, mass, matter, entropy, everything can be transformed from system to surrounding, surrounding to system. Here, nothing can be transformed from system to surrounding. That is called isolated. And when everything can be transferred from system to surrounding, then is an open system. In between, one concept is there, that is called closed system, where mass transfer from system to surroundings cannot be possible. Only energy transfer can be possible. So till now, understanding of the different kind of system with respect to possibility of mass and energy transfer are open system, closed system, and isolated system. We understood that. Now, next stage, we have to understand the state of those systems. Thermodynamics belongs to, it describes actually the initial state as well as final state, and also it talks feasibility of reaching final state with respect to certain initial state and its thermodynamic parameters or properties. And those properties and parameters also named as state variables. The state of a thermodynamic system, that's why, depends on state variables or the properties. Now, formally, if we want to introduce the thermodynamic property or definition of a thermodynamic property, it actually talks about or state of the thermodynamic system. So first we have to understand what is the state of a thermodynamic system. The state of a thermodynamic system at any instant is its condition of existence at that instant. Means the particular instant you are going to state of a thermodynamic system at any instant is its condition of existence at that instant, which specified by values of certain number of state variables or properties. What are those state variables? That can be internal energy, that can be entropy, that can be temperature, that can be composition, that can be pressure, that can be volume, that can be external field. So now we understood that a thermodynamic property of a system is actually depends on only on the state of a system, not on how the state was attained. So path is not so, it's not at all important with respect to description of a system, thermodynamic description of a system. So now again we'll understand or we'll see that state of a thermodynamic system at any instant is actually the condition of the existence at that instance, which can be specified by certain parameters value. That parameter can be named as state variables and properties. Now, what are the different properties? Different properties that can be used to describe the system or the state of the system is comprised energy, entropy, chemical composition, temperature, pressure, volume, external field, and certain case of substance size, sample size, sometimes system size, those things. So we can say that the specification of the state of the system must include the values of these properties A state of a system which can be reproduced means that state is well defined. So if you want to reproduce anything, then you have to get a proper definition of that particular thing. So that's why a state of a system which can be reproduced, it indicates that the state is well defined. So always thermodynamic state variables are well defined to describe, to represent a state. So a property of a system, that's why, only depends on the state of the system, not on how that state was attained. The uniqueness in that value of property at a state, it actually introduces naming state function for a property. So what is the important thing? The uniqueness in the value of the property at a state introduce naming state function for a property. So if you go for certain contrasting things, that the so-called path functions are quantities which concern about the path of the process by which the system changes between two states, initial states to final states, if you say. So this is the difference between path function and state function. State function represent always initial state and final state of a particular system in a thermodynamic variation or thermodynamic condition. But on the contrary, the so-called path functions actually are those quantities which concern the path of a process by which a system changes between initial state to final. Then also the final state become initial state and initial state become final state is based on that. Another set of concept will come, reversible and irreversible kind of process. Since property is a state function, its differential must be exact or perfect. Now we understand what is state function. What is state function? State function does not care about path of a process, but it also is a very different from path function. So state function does not care about the path of a process. So if we take a property of a state function, then its differential must be exact or perfect differential in a mathematical term. If you mathematically want to represent a state function, then that property of a state function should, like that, its differential should be exact and perfect differential. Why is it so? Because it does not depend on the path of the process. So state functions differentials are exact. That is very important understanding. Means if internal energy is a state function, then capital U, if it is represented, capital U represents internal energy, then the du will be perfect differential or exact differential, not partial differential, because u actually is a state function. Now we'll understand certain kind of systems. Systems are a particular part of a universe where somebody is concentrating or we are considering, and there is a boundary of this, and that can be thermal interaction can happen, chemical interaction, mechanical interaction. So that's why lot of transfer will occur and lot of constraint you can impose with respect to different kind of system or defined system. If you want to take or you want to take that system in that particular type of system. So what will be the boundary? It is open, then any interaction is possible, already we know. Then closed system, it's impenetrable by matter, but other kinds of interaction can occur, means energy can transfer. Then impermeable, so penetrable by some chemical species but not by others. All other interaction are possible. So insulated, then thermal interaction are not possible, but non-thermal interaction can occur. And if you go for a rigid, boundary cannot be mechanically deformed. So well-defined, real existence, rigid boundary we will see for such kind of system. And isolated, already we understood, no interaction can occur. Now we'll introduce Zeroth Law of Thermodynamics. Suppose in Zeroth Law it talks about conservation of the thermal energy, or you can tell that thermal equilibrium. So what it actually tells us, if two systems are in thermal equilibrium with a third system, suppose A system is thermal equilibrium with C and B is thermal equilibrium with C, then they are also in thermal equilibrium with one another. Means if A is thermal equilibrium with C and B is thermal equilibrium with C, then A and B both are in the thermal equilibrium. So what are the parameter actually indicates the thermal equilibrium? That is temperature. So if TA equals to TC and TB equal to TC, then based on the Zeroth law of thermodynamics, we can tell TA equal to TB. So we can say that Zeroth law therefore enables us to use thermometer to compare the temperature of any object we like. This is a very important statement. This law actually helps us to use thermometer and get the reading and compare the temperature between two objects. Whatever object we are want to understand what is its temperature, then this kind of measuring process is acceptable due to Zeroth law of thermodynamics. First law of thermodynamics. What it is telling, the energy of a closed system is closed system. The change in internal energy is the closed system. It is saying that is called energy as a result of heat and water. So if you say the change in internal energy is equal to W, which are state function. Internal is state function. It's of a thermodynamic system. It does not depend on the path of a process, path of the process. So you should have exact differential if you go for differential form of this equation. That's why du are exact differential and del q and del w, because q and w both are path dependent. That's why del q and del w are in the form of partial differential equation, because path dependent variable, different path dependent, different phase variable are going to influence this kind of path function. But in case of state function, like internal energy is very clear that it will have its differential form in the form of exact or perfect differential. That's why these equations in this form in the first law of thermodynamics. So be careful when you writing in the differential form of the first law of thermodynamics. Du, this should be exact differential. That two things will be partial differential. Now we'll go for second law of thermodynamics. What it is. So beforehand, you should understand that internal energy of a thermodynamic system, if you denote as U, is the sum of all macro energy of a system. It is related to the molecular structure and degrees of molecular activity, may be viewed as the sum of kinetic energy and potential energy of the molecules. So you can say that the internal energy includes the energy in all chemical bonds and the energy of free conduction electrons in the metals, because we are talking about metallurgical thermodynamics. So we will concentrate on the metallic understanding of matter. So U of a system depends on the inherent qualities or properties of the material. If you are taking care of a system, what are the inherent qualities and properties? That is the composition, physical form, as well as environmental variables like temperature, pressure, external field, system size. So U has many forms, including mechanical, chemical, electrical, magnetic, and surface, thermal, and psi ones. So that U is very important. Suppose now if you are coming into the second law, so here we are understanding the change in entropy. What is entropy? It is a degree of randomness. What is degree of randomness? If there are two kind of scenario can happen. If you increase the temperature of a system, then the vibration of the atoms with respect to its own position and also rotational and translational degrees of freedom, different things are going to get certain perturbation. So vibration will be more. So it actually adds to increment in the entropy of the system. And this kind of increment of the entropy of the system due to temperature, it known as thermal entropy. And if it due to the arrangement of the different element of the system, then is a configurational entropy. Later on, we'll understand in this class only. But del S equals to del of system, del S of system means system small amount of increment of the entropy. Now we know how entropy can be enhanced. And if you also consider the entropy of the surroundings and you sum up that, always that will be greater than 0. So second law is telling that entropy always enhance, always increases. So that is the important statement what I have represented here in a mathematically. So entropy dictates whether or not a process is spontaneous or not spontaneous. Because if through the process, if entropy is increasing, then we can tell that that process feasibility is there. It can be spontaneous. So system plus surroundings, total entropy should be enhanced through the process. Then only that process can occur. This is a very important statement, and this is the statement derived from second law of thermodynamics. Next is third law of thermodynamics. It tells it is impossible to reach absolute zero Kelvin in any number of finite process. Or in other words, I also mentioned it is not possible to lower the temperature of any system to absolute zero in a finite number of steps. So it talks about different things. So start with the process or steps. So there is no process available and it is finite and well defined by which one can reach to the temperature of absolute zero. Or you can tell that it is impossible to reach the temperature absolute zero. Why is it so? Because we know at absolute zero that the entropy is also zero. So zero entropy, if you are in order to reach zero entropy, it is impossible. It is not going to support by third law of the thermodynamics. So only it is possible when temperature is tends to zero, then the entropy also tends to zero. Next slide, we can understand that. So first start with very important definitions or concepts that gives free energy is equals to H minus T multiplied by S. G is gives free energy, H is enthalpy, T is temperature in the absolute scale, and S is the entropy. So entropy of the system. Now, if we see these things, it is actually representing the second law. How come? Because it actually tells you if the reaction or any transformation or a phase transformation occurring, then the minimization of G is required. And how G will minimize? For constant enthalpy? Only if the entropy is enhanced. So if the S is increasing, then only G will be minimized. So then the spontaneity of the reaction or phase transformation or any process will be feasible. So, and if you see in this form, H equals to U plus PV. What is H? H is enthalpy, U is internal energy, and PV, P and V, it's a work done, pressure into volume. Now, here if you see, the U is a state function, and also if you see in this respect, what is the work done? So if P and V, and if you go path 1 and path 2, different path, the work done will be different. If you see this schematic diagram, that area under the curve will be different if you go from state 1 to state 2 through path 2 or path 1. If you go path 1, you have to do more work, and if you go by path 2, you have to go for less work. So you will understand that work is a path functions. It's not a state function, and that schematic representation you can see from there. Now if you represent S tends to 0 when T tends to 0, T in absolute scale 0, then you can get the essence of third law of thermodynamics. So now in these three form of concept or representation, you can tell that mathematical representations of thermodynamic three laws you are going to understand. Now things are very simple. What is entropy? Now we understood that entropy is very important part. Then what is entropy? It is telling that degree of randomness. Okay, fine, degree of randomness. Then what is randomness? Randomness, ideally, that it is unpredictable. It's not going to be predictable. So anytime if you want to get certain things in a random number, if you want to generate, that is also a lot of functions are there. So it is totally related to chaos of a system. So in material, if you want to see the chaos or randomness inside the material, then you have to go its molecular or atomic configuration. So the atom or molecules actually come together, get certain arrangement, and makes a bulk material. So entropy, it actually degree of randomness, it takes that the element of the materials are randomly arranged. Then it goes to configurational entropy. And if the vibration of individual elements of the material in the term of molecular atom, vibration actually leads to certain fluctuation of the system, leads to enhancement of the randomness. That kind of things you can tell thermal entropy. So entropy can be represented in two things. One is thermal and one is configurational. So today class we will consider only thermal entropy, and next class we will come into discuss about configurational entropy. So thermal entropy, what is that? The ds, we know dH by T. Rather ds equal to dq by T. That was known to us. Then it can be derived. So Q by T means heat by temperature. So if we go for constant pressure, then we can tell that Q can be represented by H. So dH, So ds equal to dh by t you can write for a constant pressure condition. So constant pressure condition when you are bringing, then you also can understand there is a heat capacity concept. At constant pressure, we are not talking about not constant volume heat capacity. We are going to concentrate on constant pressure heat capacity. Why is it so? Because generally in metallurgical thermodynamics and materials behavior case, in mainly metallurgical cases, we used to consider condensed matter. We are not talk about metal vapors because the melting point of any general metals are very high. So we are not going to consider metal vapor behavior and all those things. We are generally concentrate on solid or liquid matter, constant condensed matter condition. So their constant pressure concept will be valid very easily because the impact of pressure in condensed matter is not so high with respect to the impact of gaseous or vapor of a form of a material. So here H equals to 0 to capital T Cp dt and S equal to 0 to capital T Cp by T dt. You can get this kind of formulation simply from the concept of Cp. Cp is the value. It is actually talks about that much of heat is required to raise 1 degree temperature of a unit mass of a material at a constant pressure. Okay. Now question will come. Okay. Now we understood what is Cp and what is T. Now if we can plot Cp with respect to that, it's equal to 0 if you see will be T0 Cp is slowly it will get things are known. But question will come that why Cp is 0 at 0 degree Kelvin or at absolute 0? Because there is no vibration. If you are taking a pure material, there is no vibration. So Cp are not going to get any value at absolute 0. That's why the definition of absolute 0 also talks about that at T tends to 0, the entropy will be 0. Because entropy, how you define entropy? ds. If you go previous slide, the entropy is 0 to T Cp by T dt. If Cp is 0, then entropy also 0. So at 0 degree Kelvin, the entropy tends to 0 at T tends to 0. So now we are going to ds by capital dt. So Cp by T, that means entropy always increases with increasing temperature. Why? Cp cannot be negative. Cp cannot be negative. Always ds dt greater than equals to 0. It is also telling that when you are increasing a temperature, the vibration of the atoms are going to increase and also the entropy are going to increase. Here we are not considering about configurational entropy. We are concentrating only on the thermal entropy part. So the concept of Cp versus T is, if you see the plot, it is actually telling us that Cp goes to 0 at absolute 0, and that means temperature at absolute 0 is 0. And if you go for rate of change of temperature with rate of change of entropy with respect to increment of absolute temperature, that equals to Cp by T. And since Cp always positive or equals to 0 at 0 degree Kelvin, then ds dt always greater than equals to 0. And if you talks about you should go for ds dt is greater than 0, because reaching to absolute 0 is impossible. Only at absolute 0 ds dt can be 0, and reaching to there it is not possible as per third law of thermodynamics. So today class is over. Now I am stopping the recording part. Then you